So I'm recording now. So the pre-lunch part of the lesson is really going over this paper. There are some questions where everybody kind of had the right idea, so I was happy. There are one or two questions I probably need to dwell on and spend a bit of time explaining. But as I say, it's one of these things. It's just like Hogwarts. Help comes to those who ask for it. So if there are areas where I've glossed over it rather quickly, and you really don't have a clue why the answer I gave was the correct one, stop me and ask. I'm more than happy to stop and explain something. In fact, I'd rather do that than just keep sort of ploughing on and leaving you behind in an area that you don't understand. Okay, so this is today's walkthrough, and as I said, this is being recorded, and it will be posted on YouTube. So if your internet drops out, not a problem. Just go back onto the task later on today, and hopefully your walkthrough will be up on the internet. So 75 mark paper. You always know that the last sort of few marks, it's usually between 5 and 10 multiple choice questions. At the end are usually multiple choice. They're there to make the marks up to 75, but they're also there to check for your to check that, for sort of basic understanding. But not all multiple choice questions are easy. Remember, a lot of people associate multiple choice with being easy. It isn't necessarily. Hi Yaya, how you doing? You all right?
I'm good, sir.
Okay, just going to warn you for legal reasons that we are recording this walkthrough, and it will be posted on YouTube for people to watch if they've missed this lesson, which a few people have. So we've got our we've got our data sheet. Just a quick reminder, as we've had a half-term break, you've had a week off, you've probably done some revision, but it's always good to just sort of recap. The data that's really important for Unit 2, most important ones are the acceleration of free fall and your Suvat equations. And I always give you the two most difficult ones to remember. I always give you on the formula sheets. You don't have to remember them, but you do have to remember all the Suvat equations in a way, and you have to be able to you have to be able to be able to select them, and that's really the skill with Suvat equations, is being able to select the right equation. As I say, we'll be linking to Suvat equations this afternoon when we do some work on kinematics, particularly the basics of motion graph interpretation, and I think I'll probably get on to energy transformations as well. So without any further ado, I'm wittering away here, just talking away at you. We're starting off with a simple question. Remember, question 1 is always, section A is always written answers, and question 1 is always something about units, about dimensions, about measurement techniques, and so on. So we've got a student or a pupil conducts a simple experiment to measure the speed of a toy car 1 second after it's accelerated from rest. There's a motion sensor and a data logger. So they're using something like an ultrasonic motion sensor, which can measure speed directly. Well, it measures distance directly and then calculates the speed for you. So the first part is to suggest the uncertainties of the timer. Well, I think most of us got it, so I'm not going to spend ages on it. That's to the nearest millisecond, which is reasonable for a data logger, not reasonable for a stopwatch. The speed measuring device on the data logger. So it's because there are different ways of measuring the speed. I think it's just a speed measuring device. So we've got our average, we've got our values here. You add them together, press equals, divide by 3, and the precision, sorry, I'm jumping ahead. It's 0.1 meters per second, okay? You can tell that because it's 1 decimal place. The thing to remember here when you're calculating the average is you should have the same number of significant figures in your mean as you do your actual values. You can go to 1 extra with foundation program, but as a rule of thumb, I always try to keep it the same. So for example, if I add them together, press equals, divide by 3, all I get is I end up with 2.8 to 3 and the 3 reoccurs. Oh, just let one more person in. But really, I want to call that 2.2. Little tip. You get more accurate values or more precise, more accurate values from subsequent calculations if you use your value here. Okay, if you use your more precise value. So what I do is in the space for the answer, I give it to the correct number of significant figures, but I put it in brackets underneath so that I can use it later. It just makes the calculation slightly better. So then it says calculate the percentage uncertainty in the measurements of speed. So it doesn't want the absolute one, it just wants percentage. So the simplest way to do it, remember it's range divided by 2 to give the absolute uncertainty. So it's 2.3 and 2.1, those are your highest and lowest values. So it's 2.3 highest value minus your lowest value for the same measurement, divided by 2 will give you your uncertainty, which is 0.1. But the question wants a percentage uncertainty. As we want the percentage uncertainty in the measurement of speed, we need to take that absolute uncertainty and divide it by our mean value. And I'm going to use 2.23. You can use 2.2, it's absolutely fine. Okay. And that comes out to be roughly somewhere in the region of 0.045, which if then multiplied by 100 to get its percentage, it's 4.5%. So my space for the answer, nice and clearly, 4.5%. As I marked this paper, I'm just going to give a little reminder to everybody. When you actually going through that, when you're actually submitting your answers, particularly to the 1 or 2 of you who are going to be doing your exams online, I'm just going to advise you to make sure you've written very clearly, okay? I know in a couple of cases with the papers that I've had handed in from this paper, 1 or 2 people had to give the benefit of the doubt to because they weren't clear about how they wrote their numbers. So try to make it as clear and easy to read as possible. And I know it's a bit rich coming from me because my handwriting's terrible, but it's not about neatness of handwriting, it's about the clarity of the numbers. So if you find that you're being a bit, if you find, for example, that when you write your answer, you wrote it like that, it's quite hard to see. You have to be a little bit self-critical. You've got to ask yourself, can an examiner tell what number that is? If it's not, put a cross through it and just write it a bit more neatly, and it just makes it easier to read. Okay. Remember, anything you don't want marked, you put a cross through.
Gary.
Yep.
What if question C was calculate the percentage uncertainty of the measurements of the time?
The time. Well,
Yeah.
you'd work out the uncertainty and the time, because we know the uncertainty of the time is just the uncertainty of the measuring equipment, because we've not got repeats here. So that's plus or minus 0.001. So we'd work out the percentage uncertainty. It would be just 0.001 over 1, which is 0.001, which is 0.1%. Okay. Does that make sense?
So the range in this situation is just the uncertainty of the device.
Yeah, because you've not got a range.
Sorry, the range over 2 is just 0.001. Like
Yeah,
that's what
that's the uncertainty. The point in measuring the range over 2 is that gives you the absolute uncertainty in the measurements.
Oh, okay.
Here in time, we haven't got a range of measurements, so we're just using the uncertainty of the apparatus and assuming it's been done correctly.
All right.
So it's in practice, you generally don't get that sort of thing, but you do have to work out the percentage uncertainty in the time because it comes up later on. So that's a good question, thank you. So in part D, the pupil's using a particular formula to calculate the acceleration. It's v over t, okay? So to calculate the acceleration, well, this is only worth 1 mark. This is really about the units more than the calculation, because it's so easy. You could do it in your sleep. So there's your average value. I'm putting in that extra significant figure into my calculation because it makes life easier. We know the time is 1.000 or just 1. So the acceleration is 2.23 meters per second squared. Again, I'll accept 2.2 meters per second squared. But if you didn't put the units, you didn't get the mark. Really, I was more interested in that than I was in that. So calculating the absolute uncertainty in the pupil's measured value of the acceleration. This is quite difficult. This is steps, isn't it? Okay. So first we're going to calculate the percentage uncertainty of the acceleration. So remember, that's the absolute uncertainty. So the percentage is the absolute uncertainty divided by the value. And as we've got one value divided by another, we're adding their percentage uncertainties together. Okay, so when you multiply or divide any two numbers, if you want to work out the percentage uncertainty of the calculation, you've got to add the percentage uncertainties of each number together. So delta V over V, well, it's percentage uncertainty. Luckily, in the previous question, when you worked it out, it was 4.5%. Well, actually, it's 4.545. So I'm predicting that my percentage uncertainty in T is tiny anyway. So I'm going to say 0.0454, so on. Okay. Now, I've not been clear here, so I'm going to put a cross 0.0454 plus the percentage uncertainty in T, which is the uncertainty in the value. Well, it's nearest millisecond over time, which was 1. So it's 0.4544 plus 0.01. So it's 0.046. Well, I'm going to ignore that decimal place, that decimal place there. I'm going to ignore that. So that we know now it's 4.6%. Then you take your previous value for acceleration, 2.23 or 2.3 is absolutely fine. So to get the uncertainty in the acceleration, it's going to be the percentage uncertainty as a decimal multiplied by the value of, well, it'd be 2.23 or 2.2, doesn't matter which one you use. Okay. Which you then calculate, and that comes out to be, well, when I calculated it, it came out to be 0.10 meters per second squared. So actually, if I want to, if the question asked me, and it didn't ask it this time, but you could get it in the future. If the question ever asks you to calculate the to express the value giving the uncertainty, the actual value is going to be 2.2. Now, because I've got a 0 there, I'm going to ignore it. I'm going to say 2.2 meters per second squared plus or minus 0.1 meters per second squared. And that would be the value expressed. This question did not ask for that. It just asked you to go this far. But however, just read the question carefully to check you understand what it's asking for. I'm just going to do my quick register. I've got everybody except Richard Shah. Okay. Next part says explain why using a data logger and motion sensor gives better results than using a stopwatch and a ruler. It's 2 marks. Now, this was basically for the quality of the answer, the quality of the response. So what we're really after is, why is it better? Well, the simple answer is it reduces random errors. But what causes the random errors? Well, sorry? Pascal, do you have a question?
So is it due to parallax?
Yeah, it could be caused by parallax. What I'm looking for is why it helps, and then what causes the problem in the first place. This is caused by, well, in my ideal answer, I refer to human errors, but it's not enough to just say reduces human errors, because that's too vague. So here, I think it's probably actually going to be due to parallax or due to timing. Okay, the data logger can be over 1,000 times more precise than trying to time something by hand. Okay, so it's 1 mark for a basic answer, 2 marks for something a bit more developed. Most people got 1 mark because although you had the right ideas, some people just sort of got a bit sort of stuck. And they kind of waffled a little bit or said something a bit too general. You've got to be specific. What's causing the error? Okay. Right. Then you've got your kinematics question. It is one that people struggle with. This one is a helicopter taking off. For those interested in aviation, this is an Apache helicopter. It's a military helicopter. Whenever I write these questions, just out of interest, what I do is I try to get hold of sort of ballpark values to give you in the table, so that what you're calculating is usually sort of makes sense. So the mass of the helicopter is about 8 tons. The maximum speed is 80 meters per second, and the maximum force from the rotors is about 100 kilonewtons or so. So show the resultant upward force on the helicopter is approximately 22 kilonewtons. Most of you got this right, so I'm not going to spend a long time. The resultant upward force, well, if we think about it on the helicopter, you're going to get your upward force, which is 1.0 times 10 to the power of 5. And there's going to be a downward force, which is the mass, which it said was 8 times 10 to the power of 3 multiplied by 9.81. Okay, the acceleration due to gravity. So what I would then do is I'd say, well, the force is going to be the upward force, 1 times 10 to the power of 5, minus the downward force, which is 8 times 10 to the power of 3 times 9.81. And it gives you, well, you start off with sort of an overly precise calculation to show that you actually did the calculation, okay? And then you say it's approximately equal to 22,000 newtons, which is 22 kilonewtons. Okay, so you take those steps. It's 1 mark for working out the fact you have to work out the resultant, 1 mark for having done it more or less correctly, and then sort of the last bit is really just finishing with a bit of a flourish because it completes the answer. The next one is to calculate the upward acceleration of the helicopter. So you always get this, in the first couple of questions, you can almost guarantee you'll have something that uses Newton's second law of motion. So you're using F equals ma. So the acceleration is F over m, very trivial. I'm just going to whistle through this one. I always recommend using your more precise value. But if you use 22,000 because you couldn't calculate it because that's just what you used, as long as the technique's there, you get the mark. So 21520 over the mass of 8 times 10 to the power of 3 gives me 2.69 meters per second squared, which should come out to be about 2.7 or something like that meters per second squared. Okay. As it's a calculation, it's asking me to calculate number. It's asking me to calculate. I double underline it so it's clear where the answer is. Right, now we're getting on to the more serious bit. Calculate the minimum time taken for the helicopter to reach an altitude of 500 meters. So this is using your value of acceleration. So again, the error carries forward as long as I can see working. So we're using SUVAT equations, S-U-V-A-T. So if I've got my Suvat equation, S is distance, U is initial velocity, V is final velocity, A is acceleration, T is time. I've got my distance, 500 meters. I want to work out what T is. I know what acceleration is. And I actually know from common sense what the initial velocity is. It's 0. The initial vertical velocity is going to be 0. So I'm looking for my Suvat equation, which has definitely got T, has everything else, but must not have V in it. So the only one that will do that is S equals UT plus a half AT squared. We know that U is 0 because it's taking off, so it's obviously stationary while it's on the ground. So we know that that's 0 times T, so that just disappears. So you want to make T the subject. Well, T squared is going to be 2S over A. So T is going to be the square root of T squared. Substitute 2 times 500 over acceleration. Well, I calculated it's actually be 2.69. I'm going to use 2.69. You can use 2.7 or whatever you calculated. Absolutely fine, as long as you show it and you're working. I've just had an interesting question. How do I know that that U is equal to 0? Well, it's about looking at the context of the question. It tells you it's about a helicopter taking off. When the helicopter takes off, obviously it starts off on the ground. So when it starts off on the ground, then its initial velocity is going to be 0. In a normal question, you normally get given data, you normally get given information like it accelerates from rest. But here you can see that if a helicopter's taking off, then it's obviously started off on the ground, or you can assume that, particularly if there's no other information either way. So you have to look at the context of the question. Thank you very much for asking that question. That was a good one. So calculate the upward velocity of the helicopter at 500 meters. Well, you can use all the different ones. We know S, we know U, we don't know V, want to work out V, and we know A, and we kind of know T, and you can use that, but we'll try to avoid it if we possibly can. Well, actually, if we ignore T, we end up with V squared equals U squared plus 2AS. So I want to work out what V squared is, so I don't have to rearrange this. So U squared is obviously 0 plus 2 times my acceleration of 2.69 multiplied by the distance, which is 500. And then we've got to work out what V is. So V is going to be the square root of V squared. So it's the square root of that expression, the square root of that. So that comes out to be, by my reckoning, 51 meters per second. Okay, it just comes out in the calculation, which I'm not going to bore you with. Right, this one was not as well answered, so I'm going to dwell on this one. Most people got 1 out of 2 marks. It says, explain in terms of Newton's laws of motion how the downward force creates lift. So the relevant force of motion here is that every action has an equal and opposite reaction. Okay, so that's Newton's third law of motion. So what does that actually mean? Well, the helicopter pushes air downwards, so if the helicopter is exerting a downwards force on the air, then the air exerts an upwards force on the helicopter, on the rotor blades. Okay. So we've actually then got our we've got the law of motion that's relevant, and then how it's applied. Okay. So we have to think about the law of motion and how you apply that law of motion. And that was where the 2 marks were. Most of got 1 mark. She sort of gave kind of the right answer, but it wasn't quite there. Right, it then says, during horizontal flight, the helicopter reaches its maximum speed in 30 seconds. So calculate, first of all, the average horizontal acceleration of the helicopter. So the acceleration is going to be v minus u over t. It's a CVAT equation. Okay. We know t. We don't know v. Yes, we do know v. It's 30. It's maximum speed. It's 80 meters per second because it's in the formula. It's on the data. Sorry, on the data table. It tells you it's 80 meters per second. We want to work out what a is. So v is 80. We're assuming it reaches maximum speed from rest. We're going to assume from rest. So that's 0 over t, which is 30. So it's 80 over 30, which is about 2.67 or 2.7 meters per second squared, which sounds about right. Okay, anything above about 10 meters per second squared, I think it starts to get a bit unrealistic unless it's propelled by jet engines or a rocket. So let's just calculate the average horizontal force on the helicopter. So the average horizontal force on the helicopter is going to be, well, we can use F equals ma. I think it's the simplest one to use. Force is mass times acceleration because we've got the mass and we've just worked out the acceleration, and it looks to me like a structured question. So the mass is 8 times 10 to the power of 3 multiplied by the acceleration of 2.67 or 2.7. As long as I see that calculation, I end up with about 2.1 times 10 to the power of 4 newtons. And that's your answer, okay? Probably about half the papers I received got that one right. Right, the next one. Calculate the average power used to keep the helicopter at top speed. So we're thinking about power, speed, force, because those are what we've been asked to sort of calculate before. So we know that power is the force times the velocity in the direction of the force. So if it's traveling at top speed, then it's obviously going to be the maximum force from the for accelerating the helicopter, which I calculated from the previous question to be 2.13 times 10 to the power of 4 newtons multiplied by its velocity, which is maximum horizontal velocity is 80 meters per second. So if it's 80 meters per second, that comes out to be 1.7 times 10 to the power of 6 watts or 1.7 megawatts. Okay. So that was one that quite a few people didn't attempt. That was the key there. You have to remember that formula. So this is, in order to be able to accelerate horizontally, the helicopter has to tilt forwards. Explain why. So this is one where we have to start thinking about how we make a helicopter, how the helicopter actually accelerates. So we've got to think about the idea that if it tilts forwards, then we know that the force is actually going to be in that direction. The force actually accelerating the helicopter is going to be in that direction, which means there is a horizontal component of the force. It's 1 mark, so we don't really want anything major. We just wanted the idea that this produces a horizontal component of force. Okay, that was what we wanted. I just wanted to see there was a horizontal component there. Most people actually got that one right, but I think where people didn't understand, I think there's quite a few quite a few people who sort of didn't attempt it, which is a bit of a shame. Right, number 3. This is actually an old A-level question, quite a very old one, in fact. This is the idea that we're using momentum to find the speed of an air gun pellet after it's been fired. The air gun pellet hits the block, which is sat on a trolley, which causes it to move a certain distance h above the ramp. Well done to those of you who thought about what that h represents. So a couple of you actually sort of annotated your diagram, and those who annotated the diagram did a lot better on this question than those who didn't. So this is using energy considerations. So it's all about energy. Explain how the speed of the trolley and block immediately after it's been struck by the pellet may be determined from measurements of h. Assume frictional forces are negligible. So we can say that when the trolley has kinetic energy, it moves up the ramp. And it says energy here, so energy considerations, well, this converts the energy. And it's quite all right to write KE and GPE to use the initials, because it is understood what those mean. You're converting kinetic energy into gravitational potential energy until it reaches a height h when it stops. Okay, now that might be a really good answer, but then we start to look at the bottom right here. 3 marks. Is this worth 3 marks? Not really. So maybe we want a bit more. Well, we know the formulae here, so we can work this out. We can get the idea that the gravitational potential energy converts to kinetic energy. So the gravitational potential energy at the beginning, which is mgh, is equal to the kinetic energy at the end, which is 1/2 mv squared. Okay. First things first, we cancel out the m's. And in fact, nobody actually did this. You didn't think to sort of derive a good equation, because it says how can we find the velocity, the speed or the velocity of the truck. So if it's saying how can we find the velocity of the truck, well, we know how to do this. So we end up with gh equals 1/2 v squared. So then when we rearrange it, we know that v squared equals 2gh. So v equals the square root of 2gh, where g is equal to 9.81 meters per second squared. H equals maximum height. That's it. Okay, that's what they really wanted to get the 3 marks. If you can do it mathematically, and in fact, if you did this part mathematically and just annotated each step, that's worth the 3 marks. This is actually more what the examiner at A level was actually looking for. Anyway, it then says the following data is collected from the experiment. So you've got the mass of the trolley and the block together, the mass of the pellet, which is negligible compared to the mass of the trolley, and you've got the speed of the trolley immediately after impact. So if you want to calculate the momentum of the trolley and block immediately after impact, well, to be honest, we've got everything to 2 significant figures, and this mass here is tiny compared to that. So if you're giving your final answer to 2 significant figures, we can kind of ignore it. You can put it in if you want. So you can say 0.502, because we're adding the 20 grams, so the 2 grams into the equation there, multiplied by, that's the mass, multiplied by its velocity, which is 0.4, which gives you 0.2008. Well, all the values here are to 2 significant figures. So I'm going to give my final answer to 2 significant figures. So we've got to include the unit, which is going to be for momentum. It's kilograms meters per second.
Very.
Yeah.
Please explain that again.
Which one?
This question.
This whole question. So the idea is that the pellets hit the trolley and embedded into the block. Okay.
Okay.
So obviously, we want to work out the momentum of the trolley and the block immediately after the impact. It's the mass of the trolley with the bullet multiplied by its velocity or its speed as it's shown here. Okay.
Well, how come when they were saying the speed, they just said the speed of the trolley and the block, they didn't say the trolley and the block and the pellet?
Well, to be honest, it makes no difference. Even if you just use 0.5 here instead of 0.502, you end up with the same answer.
All right.
Okay, so it actually doesn't matter in this case. Now, if you've got all your values here to 3 significant figures, you'd need to add it because it does tell you, that the pellet embeds itself. That means it gets stuck inside the block. Okay.
Yeah.
So you've got to, so technically we should include it. But in this actual question, it doesn't actually make any difference.
Okay, thank you.
So then you want to work out the speed of the pellet just for the impact. Well, we know that the momentum is 0.20, okay? Or 0.2008 if you want. Doesn't matter which one you use. That's going to be the momentum, which is the mass of the, which is going to be equal to the momentum of the bullet beforehand, because the truck isn't moving a bit before it gets hit by the block, before it gets hit by the bullet. So because the block isn't moving, its momentum is 0. We've only got the momentum of the bullet to worry about. So that's going to be the mass of the bullet multiplied by its speed, v, which is what we want to work out. So to get the speed, it's 0.2008, when we could ignore that bit if you want, 0.002, which gives you 100.4 meters per second. Well, we'll just say,
Gary, isn't that the momentum of the block?
It is, but if we think about the experiment here, remember momentum before is equal to the momentum afterwards. So beforehand, the block's stationary, so the only thing with momentum is the pellet or the bullet. Afterwards, the bullet and the block and the block and the trolley are all moving up, and they have their own momentum, which you've worked out here. So because we take this to be an isolated system, because there are no other forces being sort of mentioned here, no external forces, we therefore can assume that the momentum of the pellet before it hits the block is actually the same as the momentum of the block, trolley and pellet together after it's hit the block.
All right.
Okay, because of the law of conservation of momentum. So we calculated before the momentum of the trolley and the block and the bullet, 20 kilograms meters per second. So that will be the momentum of the bullet, sorry, 0.2, I do apologize. That would be the same as the momentum of the bullet before it actually hits the block. So the momentum of the bullet is the mass of the bullet times its speed, so we can actually work out the speed of the bullet. Does that make more sense?
Thank you.
Okay. Right, state what is meant by an inelastic collision. Well, the simplest way to put it is the kinetic energy before is greater than the kinetic energy after the collision. Or you can just say that kinetic energy is not conserved. That's absolutely fine. So the next part really says use the data from part B to show the collision between the pellet and the block is inelastic. Now this one was not very well answered. What you do is you do before and after. So before the collision, we know that the kinetic energy is a half mv squared. So it's a half times the mass of the pellet, which is 0.002, multiplied by its speed, which is 100 squared. Comes out to be, well, more or less 10 joules. Okay. And then afterwards, we know it's a half mv squared, a half times, well, it's the mass of the block and the bullet and the trolley together. Again, if you ignored the mass of the bullet, it's not a problem. It still comes out. 0.502 is the new mass, multiplied by its speed, which it told you was 0.4 meters per second. Okay, it told you earlier on in the question that it moves off at 0.4 meters per second. So if that's the case, we can then say, we can plug that into your calculator. It comes out to be 0.04 joules. So it is inelastic.
Gary, so an elastic collision is just a collision where the bodies don't move after colliding.
No,
Is that what
elastic
an
collision,
elastic
collision where the kinetic energy is conserved. So the kinetic energy before is the same as the kinetic energy afterwards. Here they're not, so it's inelastic.
So it doesn't matter how they move after they collide.
There is another, it does come out in the wash that if you have two bodies colliding and they're colliding with as an elastic collision, ignoring the mass even, that's initial velocity u2. The sort of the relative velocity between the two here is going to be u1 minus u2. Imagine that they collide and they start moving apart. So this one's now moving in that direction. That one's moving in that direction. What actually happens, well, it actually could be moving in that direction, actually, just as easily, I do apologize, is that the relative velocity that they actually recede by, actually now moving apart, because these are moving together because they collide, and then afterwards they're moving apart, even though this one might be moving more slowly than that one, it's still, those two values turn out to be still the same, but that's going into a level that we don't really need to worry about. So if you don't understand that, don't worry about that too much, okay? Because it's not really in the syllabus. What is in the syllabus is the idea that in an inelastic collision, kinetic energy before is not the same as kinetic energy afterwards. Some is lost. For an elastic collision, the total kinetic energy of everything before is equal to the total kinetic energy of everything afterwards, okay? Does that make sense?
Yeah, thank you.
Okay. Right. Next one. Now, those of you who attempted the next one did quite well with it. Just the thing to remember here when you're calculating, I'm not going to sit and calculate them in front of you because I think that's just boring. I think you'd fall asleep. Hang on.
Should go for lunch and return in 45 minutes.
Right, sorry about that. So speed squared here, everything's two significant figures. You can get away with three significant figures here, but no more than three. Okay, I use three. Some people prefer to use two. It doesn't matter. Here again, we've got two significant figures or three, so we should be using two or three in our answers, in our mean calculations. It's 3 marks. 1 marks for correcting this column, calculating this column correctly. 1 marks for calculating that column correctly, and then a third mark was for getting the significant figures correct in both columns. It then said to use the graph paper to measure v squared to draw a graph of x, the range, versus v squared on the x-axis, and draw a straight line of best fit. So when you drew it, when I did it, this was the scale I got. So I'm just going to zoom out slightly. Oops. Bear with me. Right, okay. Now, what I got here was, I first of all worked out that I can't really go through the origin here, okay? So I'm not, yeah, because it wouldn't fit on if I tried to sort of get it to go from 0. So I started at 200 as my v squared. Absolutely fine. You don't have to put the origin on unless the questions, when you look ahead, don't seem to ask for it. The thing to remember here is that you then sort of put an appropriate scale. So I'll look at my scale. There's my bottom value here. There's my top value here. And we know that sort of we're making good use of the entire space of the graph paper. As long as you're using more than half, it's fine. The other thing to remember is, of course, the units with the labels. So it's name, symbol, unit, or at least symbol and unit, symbol and unit. And then you get 1 mark for plots, and they should all actually line the line of best fit in this particular case. They don't always, but they do in this case. Now, the other thing to remember here is about scales, and I'm just going to mention this because 1 or 2 people presented graphs to me which had funny scales. Remember, scales should be easy to read, so it should be 80 to 100, so that represents maybe 20 meters, not sort of going from sort of 60 to 90. If you go up in 3s, it becomes very, very difficult to plot the values correctly. So if you go up in 3s on your scale, that's an inappropriate scale and you lose a mark for it. So you've got to remember to use an appropriate scale, going up in 1s, 2s. You can just about get away with 2.5s. You can get away with 4s, going up in 4s. You can get away, and it's fine to go up in 5s and 10s and so on. But if you're going up in 3s, or the worst one I've seen was going up in 7s, that wasn't any of you, but I've seen it in the past, trying to go up in 7s or something like that, that's when it becomes really difficult to read, so don't do it, okay? So we stick to a simple scale. Remember, you can also, in some cases, turn your graph paper on its side, if that helps. Most people who did the graph did it correctly, so that was fine. I'm not going to spend a long time on that. You then have to calculate the gradient of the graph. So if you're asked to calculate the, oops, get rid of some of these sheets here. You're asked to calculate the gradient of the graph. Again, you're finding convenient points on your graph. Word of warning, do not use data points to measure your gradient. You should be using your line. So don't put your triangle points on a data point, because then it's not certain whether or not you're actually measuring from the line or from a data point, okay? And your triangle should be nice and big, okay? It should be taking up more than half of the space of the line. So if you imagine that's the space, that's the distance between from first to last point there, it should be more than half of that distance, which, if as I measure it, yeah, it's more than half, that's absolutely fine. You label y1, y2, x1 and x2, and you read them. So here I'm going up in 20s, so each small square goes up in 2, so it's 122, 40, and so on. I'm not going to spend too much time on that. As we go through it, we then look at the question which says calculate the gradient of the graph. So you've drawn your triangle, you've shown your y1 and y2. This is part of answering this question. You can kind of predict that you will get this kind of question. You nearly always do. There's nearly always a graphing question in UFP exams, physics exams. So the gradient, remember, is delta y over delta x, which is y1 minus y2 over x1 minus x2, which when I measured it, my upper y value was 122, my lower one was 40, over 1,200 minus 400. I get 82 over 800, which is about 0.102 or something like 25, something like that. So now it says give appropriate units. So I go back to my graph. it's the units of y divided by the units of x. So the units of y are meters, the units of x are in meters squared per second squared. So if I rearrange that, if I simplify that, it's meters to the minus 1, seconds to the power of 2. And there's my answer. It then says it suggests the formula shown below gives the relationship between range and speed, where g is the acceleration due to gravity. So that's my range x, that's my speed squared there. You should be able to compare it with y equals mx. That comes up later. But the first bit says show that the horizontal and vertical components of the velocity are given by these two formulas. So the horizontal component, if you've got velocity v, that's got a horizontal component and a vertical component. And that angle here is 45 degrees. So there's a couple of ways of doing this. First of all, if it's a 45-degree triangle, so we'll show you the two basic methods. The first method one, which is acceptable, is to say, well, if it's a 45-degree triangle, actually those two distances are going to be the same. Okay, so if we think about it, v squared is going to be v8 squared plus v squared, because you're using Pythagoras theorem. As the two of them are the same, v squared is going to be 2v8, which is the same as 2v8 squared, 2v squared. Okay, so in this case, if we rearrange it, v8 squared is going to be v over 2, so we square root it. It's going to be v over root 2, and the same with vv, that's also v over root 2. That's one way of doing it. Okay, the second way of doing this, that's absolutely acceptable. The second way of doing this is to use trigonometry. We know that v is going to be v, well, that's the opposite, so that's going to be v sine theta. Okay, and we know that vh is going to be v times the cosine of theta, the angle, 45 degrees. Well, those of you who are good at mechanics, the sine of 45 degrees is 1 over root 2. Okay, same with the cosine. The cosine of 45 degrees is 1 over the square root of 2. So we end up with v equals v over square root of 2. vh is equal to v over the square root of 2. Okay, so what we've got there are two different methods of doing the same thing. It depends whether you use Pythagoras theorem or whether you use trigonometry, sines and cosines. Okay, so that's how you do that. Okay, so as I move on, it then says suggest whether or not the data and graph support or undermine the formula shown. So does it support it? Undermine means it doesn't support it. It disproves it. Well, let's go back to this. If we've put x on the y-axis, we put the range x on the y-axis and v squared on the x-axis, which is what we did. We end up with, if g is a constant, we end up with a straight line through the origin. So the graph shows that x is proportional to v squared, which would imply a straight line through the origin. Okay, and therefore, as the graph shows that, it supports the theory. Okay, that's why the graph supports the theory. It's the right shape. So it's 1 mark for
Very.
identifying that it should be a straight line through the origin, and 1 mark for then saying that it supports the theory, because that's what it is.
Gary,
Yep. Yes.
how does the graph being a straight line through the origin support the theory?
Well, if you look at the formula, remember when we said before about y equals mx plus c, okay? That's a formula for a straight line graph is y equals mx plus c. Here, that c is 0, so the y-intercept would be 0. So if you whatever you put there on the y-axis and whatever you put there on the x-axis, if this part of the formula here is a constant and g is a constant, it's not going to change in the context of this experiment. So that's a constant, which means the gradient's constant. So we'd expect a straight line through the origin because it tallies with y equals mx plus c. Does that make sense?
So it's basically because the y-intercept is 0.
Yeah. And the fact the most important part is the fact that it's a straight line. It's proportional. Okay. Right. Then it says using a value for the gradient, calculate the acceleration due to gravity. Well, if we look at our formula again, I keep going back to this sheet. We know that our formula shows the gradient of the graph is going to be 1 over g. So you write that, you then rearrange to make g the subject. Well, that's pretty much a no-brainer, which is equal to 1 over 0.1025, which comes out to be, well, when I did it, it was 9.76 meters per second squared, okay? Now, it obviously, the important bit is that it's 1 over the gradient. That's the bit that I'm looking for, the recognition it's 1 over the gradient, and then an attempt to calculate it. So as long as you put your value for the gradient here, you'd get the mark. It doesn't actually matter too much what this number comes out to be, as long as it's in the right ballpark. I'm expecting a number within a certain range. Okay, everyone? And that is the big graph question. As I said before, that graph question, it can be anything up to a quarter of the marks on your paper. So it's really important to really get used to doing them. Right, number 5, state the difference between a scalar quantity and a vector quantity. And it's the easiest 2 marks of your life. So the best way to do it is to define them. So a scalar quantity has magnitude, size, but no direction. Has a size but no direction. A vector quantity has size or magnitude, and direction. If you made a sort of a statement explaining the importance of direction with vectors, I gave you 1 mark. If you really sort of defined them both clearly, I gave you 2 marks. Again, that second mark really was for quality of written communication. Now, the next part was interesting. Very few people actually attempted this. I think it's because of quite a few of you don't yet have protractors. What you need to do with this is, if you read the question carefully, it tells you've got 2 forces, magnitude 6 newtons and 8 newtons, act at point P, and both forces act away from point P, and the angle between them is 40 degrees. So what you're trying to do is work out the resultant. Now, some of you tried to use trigonometry. The question was very clear. It said by drawing a scale vector diagram. So if you're drawing a scale vector diagram, that angle there is 40 degrees. You've got your 8 Newton force, which is horizontal. So first of all, I'm going to set up a scale. I reckon I can fit this in if 1 centimetre was equivalent to 1 Newton. Okay, So if I draw my first diagram, I think they're up in the ante outside the building site. If I draw my first diagram, I'm going to make it 8 newtons, so it's 8 centimeters long. And then I'm going to put a dotted line. I'll show you why that is in a second. Okay, so that's my 8 newtons vector. And the next one is a 6 Newton force at 40 degrees, shown there. So if I take my protractor, put my point there at the end of my vector, so it's end to end to work out the resultant. I've got my 40 degree angle there. Okay, that's 40 degrees. And this is 6 newtons, so I'm drawing a 6 centimeter long line. So I take my ruler and I draw a line as close to 6 centimeters as I possibly can. I draw it as accurately as I possibly can. Starts at 6, ends at 0. There we go, lovely. So that is then the 6 Newton force. So what I want to do to work out the resultant is always from start to finish. So the magnitude of the resultant, I'm not interested in the angle, thank goodness, but it would be trivial to measure it, is the resultant is actually that arrow there. Okay, which I can measure on my scale because all vectors behave the same way. So let's put my 0 right at the end here, try and avoid any parallax errors. Here I've got 13.3 centimeters. Okay, so here I make it 13.3 newtons, or I could just say 13 newtons. Again, that can be a little bit out, not a problem. It's not a problem if that's a tiny bit out, but what can be a problem is if we forget to put the arrows end to end. As long as there is a decent amount of sort of working, if you draw that scale diagram, you've selected a scale, you've clearly drawn it, you're getting 1 mark straight away. It's a 4-mark question. So you get 1 mark for just kind of selecting a scale, 1 mark for drawing it with the arrows end to end, 1 mark for measuring the length of the resultant, 1 mark for converting it into newtons and putting something that's about the right answer. Okay. Not an easy one, but then not as hard as it looks. This one was very interesting. This is our moments question. You get a question about vectors. You'll get a question about moments. So we've got a supermarket trolley. Again, this is actually an old exam question, an old A-level exam question. The weight of the trolley and its contents is 160 newtons. First of all, what is meant by centre of gravity? Hello, 2 marks. We're looking for a little bit of precision here. And it's centre of gravity, not centre of mass. So if we want to define centre of gravity, it is the position or the point at which all the weight of an object can be said to act. Okay, if you said mass of the object, you got 1 mark. If you said weight, you got 2 marks. Okay, that's a definition. Okay, centre of gravity and centre of mass, they have definitions. Look up, make sure you've learnt the definitions. You're then told that P and Q are resultant forces that the ground exerts on the rear wheels and front wheels respectively. Calculate the magnitude of force P. So if we want to work out the magnitude of force P, what we're doing is we are using that sort of bridge, that physics, same physics we use for calculating the force upwards from a bridge. So the first thing to do for calculating the force at P is to take the moments at Q. So we take the moments about Q. So we know the force at P multiplied by its distance from the pivot. So the distance if we take Q to be the pivot, then the force from P is going to be an upward force multiplied by this distance here, which is 40 times 50. You can convert it to meters if you like, but seeing as everything's working in centimeters, I'm not going to bother. So I'll say P times 90. So that's the clockwise moment. The anti-clockwise moment is caused by the weight of the trolley. So the line of action of the weight is here. So the distance between the line of action and the pivot is 50 centimeters. So that's going to be the distance of 50 centimeters multiplied by the weight of the trolley, which is 160 newtons. Okay. And we can work it out. It comes out to be 89. Okay. So P equals 160 times 50 over 90. When I did the calculation, it came out to be 89 newtons. Now the force at Q, we can use the other condition for equilibrium. That's rotational equilibrium, is that clockwise moments equals total anti-clockwise moments about a point. Force Q, we can use the other condition whereby the total upwards force equals the total downwards force. So the total downwards force here is going to be just the weight of the trolley and its contents. The upwards force is going to be provided by P and Q. So the idea would be that the downwards force, which is 160 newtons, is equal to P plus Q. And we know what P is, it's 89. So Q equals 160 minus 89, which gives you, by my reckoning, 71 newtons. Okay. You could do it by taking moments about P. You could do it that way. It's absolutely fine, and you'd get exactly the same answer if you did it correctly. I just think this is easier. So the next one then says calculate the minimum force that needs to be applied vertically at A to lift the front wheels. So we've all done this one when we've been shopping. We've sort of lent on A. We're trying to look at the force being applied here. Okay. And if we lift the front wheels, then P is the pivot. So we're taking moments about P, because the whole thing is it's meant to be that the trolley's lifting up. So when it's being lifted up, we've got a pivot point here. So all we have to do really is calculate the minimum force that's needed. So we've got the minimum force that's needed. Well, the minimum force needed, that's going to provide an anti-clockwise moment. So that's going to be the force at A multiplied by the distance between A and the pivot. Here it says it's 10 centimeters. So force times 10 equals the clockwise moment. Well, if the wheels are off the ground, Q isn't providing a force anymore. So if that's the case, you're applying a force downwards. The upwards force is going to be from the center of mass. So that's 40 centimeters away. So that's 160 newtons multiplied by 40, which means the force is going to be 160 times 40 over 10, which is 640 newtons. Okay. Right, now this one for 3 marks, you have to be very careful. It says state and explain without calculation how the minimum force that needs to be applied vertically at A to lift the rear wheels off the ground compares to the force you calculated in part C. So if we think about it, if we're trying to lift these rear wheels up, we're applying a force from A here. The pivot is over here. So instead of being 10 centimeters away from the pivot, we're now a meter away from the pivot. Okay. So as we've got a greater perpendicular distance, we can provide a similar moment with less force. So the force at A is less. Due to the force being further away from the pivot Well, it's the new pivot, isn't it? At, well, we call in here in the question, they called it Q. So I'm going to call it Q. At Q, okay. Or between A and the front wheels, you could say, okay. So a greater moment can be provided with less force. Okay. And that's your answer. Okay. It's the idea that you've got a greater perpendicular distance between the pivots and the force here, and therefore you need less force for the same movement, or even indeed there's less, even less force for to provide a greater moment. So, I mean, you've probably experienced that when you've been shopping. If you get a shopping trolley, if it's full of stuff, if you can probably lean quite heavily down on the handles before the trolley tips up backwards. But if you want to lift up the rear wheels for any reason, you can usually do that quite a bit more, quite a lot more easily. Okay. Now it doesn't want calculations because it specifically states in the question without calculation. Right. I'm aware of time. We are nearly done. So for the multiple choice, so it says physical quantities can be classed as vectors. Which pair consists of two vectors? So kinetic energy is a scalar, so that's not a vector. Time is a scalar. Velocity and electric field strength. Well, we don't know what electric field strength is, so we're not sure. So let's go to the next one. Rate and temperature. Well, temperature is a scalar, so it must be C. Okay. Even though we don't really know what electric field strength is, doesn't matter. So part A here, a tennis ball falls freely in air from the top of a tall building. Which graph represents the variation in time with the distance falling? Now you've got to be careful. If it's in air, you have to think about air resistance. So we know the velocity will decrease over time. But this is a distance time graph. S is distance. Okay, it tells you in the question, S is distance. So a lot of people select this one because they think the speed goes up until it reaches terminal velocity, but that's not what the graph is. What it was saying is the speed increases, the acceleration will decrease over time until it's straight, until it's constant velocity. So which one has an increasing gradient? Because the gradient of a distance time graph gives you the speed. Okay. So the gradient of a distance time graph gives you the speed. We know the speed's going to increase and end up constant. So we're looking for something with an increasing gradient until the gradient's constant. Well, that's pretty much a straight line there. And that's a curve with increasing gradient. So the answer was A. Number 9, the graph shows the variation with mass of the weight of objects on a particular planet. If to calculate the acceleration due to free fall. So the simplest way to do it is to know that, to recognize that as being 2.5, and that's 4. So G is going to be the weight, the force over the mass, which is 4 over 2.5, which comes out to be 1.6 meters per second squared. Right, number 10, cannonball of mass of 3.5 kilograms is fired at a speed of 22 meters per second from a gun on a ship at height 6 meters above the sea. Blimey. The total energy of the cannonball is the sum of the gravitational potential energy relative to the surface of the sea and the kinetic energy. So what is the total energy of the cannonball as it leaves the gun? So this looks horrible, but it's actually pretty easy. We're just adding gravitational potential energy to kinetic energy. So the kinetic energy of the cannonball is a half mv squared. So it's a half times 3.5 times 22 squared plus the gravitational potential energy, which is mass times gravitational field strength multiplied by the height. So that's going to be the mass is 3.5 multiplied by gravitational field strength, which is 9.81. It's on the formula sheet, multiplied by the height. It tells you it is 6 meters above sea level, so it's times 6. You calculate it, you work it out and you calculate it, it comes out to be 1053. Any one of those close, well, that one's pretty much on there, so it's D. Right, next one, an aircraft travels at a velocity of 90 meters per second in horizontal flight. So it's a constant velocity, and it's doing work against the drag force there of 2,400 newtons. You're given the mass of the aircraft, but you don't need it, because you know that power is force times velocity. And if the power is force times velocity, we know the force is 2,400 multiplied by 90, comes out to be 210,000 watts. So we're looking at somewhere in the region of, well, 2.2 times 10 to the power of 5 watts. A lot of people clicked on select that one because it's the same, because that's 2.0, and while you could argue that's 2.0 there, because it's 216,000, I do apologize, but actually it's the wrong power. Owen.
Is the drag force the same as the thrust force because it's traveling at constant velocity?
That's correct, yes.
Okay.
Okay. All right, almost there, almost there. Right, last couple of questions, and then you can go and get some lunch. So we've got a ball is released at rest from above a hard horizontal surface. The graph shows how the velocity of the bouncing ball varies with time. At which point on the graph does the ball reach its maximum height after the first bounce? So we're looking at a velocity time graph. So what's happening? The ball's dropped here. It's increasing in velocity downwards until suddenly it reverses. So that's the point at which it's bouncing. So that's when it's on the table, okay? When it's on the horizontal surface. Once it then finishes bouncing, it's then moving upwards. So it's got a negative velocity, and that negative velocity is decreasing all the way to 0 when it then becomes a positive velocity. It then becomes a positive velocity. So there it's moving back downwards again. So where it's moving upwards and changes to downwards, when it reaches its maximum height after the first bounce, it's going to be there, C. Okay. As I say, I'm going to do a masterclass on the motion graphs, I think, because I think that's something that we just need to be we need a bit more practice on. So a ball is kicked upwards at an angle of 45 degrees to horizontal. After a short flight, it returns to the ground. You can assume air resistance is negligible. In other words, you can ignore it. You have to ask what is never 0 during the flight of the ball. Okay, a horizontal component of the ball's acceleration. Well, no, the ball's acceleration is going to always be 0. Okay, because the horizontal component of its initial speed becomes its horizontal component of acceleration because we're ignoring air resistance. So it's not A. The horizontal component of the ball's velocity. Well, if we think about it, it's always going to have a positive velocity. It's not going to stop. So actually B is the answer. But as with multiple choice, we check the other answers just in case. So part C, the vertical component of the ball's momentum. Well, if you think about it, if the ball's going upwards, it goes back down again. So at some point, that vertical component of its velocity and therefore momentum, when it gets to the top, is going to be 0. So that definitely is 0 at some point. So B is the one value there that is definitely not 0. Okay, and that is the paper. Okay, any questions? Anybody at all? Okay, so what I'd like you to do, I'd like you to, you can go and grab your lunch, and if we log back in, please, at 1:40 this afternoon, I'll do some work on, I will do some work with you on the motion graphs. Okay, I'll see you this afternoon.